Okay, let's get started. So welcome everyone to this workshop. I'm Umesh Vazirani. I'm the director for quantum computing here at the Simons Institute. Most of you here probably know about the Simons Institute already. It's one of the it's a marvelous place for doing interdisciplinary work that's based around theoretical computer science. And one of the one of the best examples of this is the Quantum Research Pod, which hosts postdocs, senior visitors at all times, but also hosts things like the semester-long program and this workshop. The Quantum Pod is funded by NSF and DOE, and through the National Quantum Initiative. So just a few things for those who don't know about this place. So a couple of logistical things. You're on your own for lunch. You should try to avoid bringing in any drinks and food into the auditorium. And let's see if any of you are active in social media. You know, that tells you what to do. Okay, now just a little bit about this workshop. One of the things these Simons workshops are known for is for being really up to date. You know, the schedule is not decided until very close to the event, and this is not through sloppiness but by design, just to make sure that these are the most up-to-date and interesting talks. And what this does is it places quite a burden on the organizers of the workshop. Marcus Müller and Nico Bergman and Bill Pfefferman did an amazing job. You know, they put in a huge amount of work behind the scenes to make this happen. So thank you for doing that. And so with that, I'll turn it over to Marcus, who will actually introduce the workshop.
Yeah, thank you very much, Umesh. And also a warm welcome from my side. I'm Marcus Müller from Aachen University and the Research Center in Jülich in Germany. It's great to have you all here for this workshop on near-term quantum computers, where I think we'll have a very exciting program ahead. We had the pleasure to put this together with Nico and Bill and Umesh. Just to add on or a little bit out of an outlook, what we'll be having are 5 days of, I think, exciting talks, but also hopefully a lot of exciting discussions in the coffee breaks after the end of the official program. Today we'll be mostly focusing on quantum error correction and fault tolerance, where I think we'll be hearing that we are entering the era of early fault tolerance. Tomorrow will then be dedicated to benchmarking and characterization of quantum devices, which also brings really a challenge where, in view of the increasing system sizes that we have to face. On Wednesday, we'll be focusing on quantum algorithms, and then on Thursday and Friday on quantum advantage, new applications, new approaches. And also with a panel discussion then on Thursday. With that, I hope I did not forget anything. I forgot one thing. So I'm coming from Rabi frequency land, from quantum optics, AMO physics. This is a workshop with a lot of theoretical computer scientists. So please keep that in mind, that we somehow also want to bring together here theoretical computer scientists with physicists. So keep the use of Rabi frequencies, laser intensities, and so on, really to an absolute minimal level that you need, so that we hopefully find a common language and have a good discussion going on. And with that, without further ado, I hand over to Stephen Bartlett. It's my great pleasure to have you here and starting the workshop. Stephen with a talk on quantum error correction and fault tolerance from Sydney University. Thanks.
Thanks, Marcus. Is this on? Yes? Okay, and thanks, Umesh, and thanks to Nico and Bill for putting together this workshop. So I'm Stephen Bartlett. I'm from the University of Sydney. That's me. just indulge me for a bit as I tell you about what we're seeing here in this picture. This is a model of a distance 7 3D color code, which is a particularly interesting topological stabilizer code. Okay, so that's a little piece of jargon, but for those of you who work in topological stabilizer codes, you know that all of the interesting properties are captured in the boundaries, in the boundary conditions. And so we found this model, we found this code quite difficult to sort of think about and work out its properties until we actually put together a model. And we didn't have to build it that big, but that's how many pieces we had, and it was fun to put it together. Ben Brown did that actually over a long weekend, and it turns out to be a beautiful, I think, piece of art, but also very useful in understanding properties of that code that we play with. And I'm super excited because our university has a museum. They're putting on an exhibition about models in research and education, and they saw our models and they said, we want to put this in the exhibit. So this is going into a museum later this year, and that the only downside to that is if you come and visit Sydney, you can't grab it and play with it anymore because you're not allowed to touch the pieces in the museum. Okay, so with that bit of introduction, I am going to talk about quantum fault tolerance, and I was asked to give, since it's the first talk on this day devoted to error correction and fault tolerance, to give a bit of an introduction. So it's going to be my perspective on where we're at with error correction and fault tolerance, and given that we're all theorists here, I think. Almost? No.
We have also experimentalists here on board, yeah.
Oh, okay. I was asked to give a talk for theorists to think about what are the interesting theoretical questions at the moment in quantum error correction and fault tolerance. So that's going to be a bit of my perspective, and if I have time at the end of the talk, I'll get to some of the work that we're currently doing in Sydney in that direction. So bear with me if you are a researcher in error correction and fault tolerance. Some of this will be a bit old hat, but for those of you coming from different fields, I'm hoping that this gives you some context for some of the other things you're going to hear about today and later this week. And by all means, jump in and ask questions during the talk if anything's not clear, because it's meant to give you that introduction. I called it Dawn in the Age of Quantum Fault Tolerance because, well, first of all, I think we are going to see an age of quantum fault tolerance, that the useful quantum computers, the useful applications of quantum computers we're going to see are going to require fault tolerance. And so this age is going to last for a while as we build fault-tolerant quantum computers and start to use them for interesting problems. And for the few of you in the audience like me who've been in this field for 20-something years, you might say, why are we calling this dawn? Well, it does feel like a bit of a dawn, because what's changed in recent years is a lot of developments on the experimental front in hardware, in actually putting to action a lot of the theoretical work we've seen over a while in quantum codes in fault tolerance. And so we're starting to see that really come to fruition. And of course, that's injected a huge amount of excitement and energy into the field as we start to build fault tolerant logic. And so I think of this really as a dawn. The sun is finally rising on seeing some of these ideas come to light. Okay, so this is meant to be an overview, as I said, from my perspective. Super high level. Okay, practical quantum computing here. Quantum computing that solves useful problems. That's actually a key question. What do we need to solve useful problems with quantum computers? Maybe we can do that now, but I think we would all agree that many of the interesting problems, algorithms that we look at for quantum computers are going to need larger circuits and more qubits, more depth of the circuit than what we have available today. So our current technologies are failing too frequently in order to be able to run most of the interesting things. As a sort of a general rule, the error rates that we see in hardware today is sort of at a fraction of a percent, maybe a small fraction of a percent, but to run things that would involve thousands or millions of qubits and deep circuits, that's without error, that's quite a bit out of reach. The hardware is improving, but it's not like we expect those error rates to go from a fraction of a percent to 1 part in 10 to the 10. That's very unlikely to happen unless there's a really amazing breakthrough on the experimental front. Not unheard of. I mean, we have classical technologies that work with error rates even much better than that, but I don't think there's an expectation that we're going to be able to push the hardware into that regime. Okay, so we need to somehow figure out a way to use relatively noisy hardware to do more complex circuits, deeper circuits, and run more interesting algorithms. And that's where fault-tolerant quantum computing comes in. And I really view this as a catch-all term. Fault-tolerant quantum computing is not a specific thing. It's a general approach to how we might use those noisy quantum devices to execute large-scale quantum computations using faulty parts. Okay, and I'm going to try to give you an introduction to that whole concept of this field of fault tolerance. Okay, so those of you maybe not so familiar with the field, but sort of paying a bit of attention might look at things this way. Well, we've got physical qubits. They're noisy, as I say. They fail a fraction of percent of the time. What we need to do is find a good quantum error correcting code and make logical qubits. And those logical qubits should be near perfect. Maybe those are the things that fail once every 10 to the 10, maybe 10 to the 15 times, depends on how big an algorithm we want to run. But failure rates such that we can run a whole complex algorithm without failure, with high probability. Okay, what I want to get across today is that this is an incredibly simplistic picture. And there's much more to it than just saying, let's use quantum error correction to take physical qubits to logical qubits. Okay, and in preparing for this talk, I was just looking at some things that have been out there on this topic recently. And I found something in this room. Jungwon gave an amazing talk just 2 months ago. Was anyone here for that? One person? 2 people. Fortunately, it's on YouTube. A great talk. I encourage you, if you're interested in what I'm describing here today, you should definitely watch Jungwon's talk as well. He really looked at experiments that are being done now, where people are claiming to have created logical qubits in hardware, where people are claiming to demonstrate logical gates in hardware, and really taking a really interrogative lens to those claims and saying, what have we really done and what do we need to do in order to get to that promise of achieving fault tolerance? Okay, so it's a great talk, and I'm not going to attempt to repeat all of that there, but I do want to acknowledge I've taken a little bit of inspiration from some of the things that Jungwon said in his talk in what I'm going to describe today. Okay, so this picture, though, is a little bit simplistic. So let's see if we can unpack that a bit. Okay, can we make quantum logic occur with error rates that are much less than the error rates of the physical hardware that we're using? Well, we have a great theorem, the threshold theorem, that tells us, yes, this is possible in principle. And it's impossible, actually, with not a very significant cost. Of course, the devil is in the details. Okay, so what it says, what the threshold theorem says, is that if your physical error rates are below some threshold, they're low enough, and the noise is sufficiently uncorrelated or behaves nicely, then I can I can simulate a perfect, arbitrarily large computation with this noisy hardware with just a bit more overhead. You notice that that statement, as I just sort of described it loosely there, doesn't mention logical qubits. It just talks about being able to do long computations with noisy physical qubits. Okay, now, as I said, a lot is in the details. Sorry, question?
You used the word simulated.
Yep.
Why? Like, why using the word simulated there and not like computing? Oh, sorry. Yeah, why using the word simulating there and not computing?
Okay, well, why am I using the word simulated? I mean, precisely what the threshold theorem is saying is that you want to take a certain perfect circuit that you want to execute, and now I want to use my faulty hardware to run that circuit. So it's not going to run exactly that circuit. It's going to run a different circuit. It's going to run a fault-tolerant circuit with a bunch of error correction in it, but that the output of that circuit is going to be the same as the desired one I want to get. So that's what I mean by simulate in that sense. And maybe that's not quite the right word. Okay, how do we do that? As I said, the devil's in the details. That will depend on the choice of code, but many other things, such as how we use that code, how we do error correction, how we measure for errors, how we correct for them. It depends on the physical nature of the errors. It's not enough to just specify your code. You have to say, how am I going to do all of that quantum logic in a way where I'm using noisy gates to do the logic and also to do the error correction. So we say that with those logic gates, using this quantum error correcting code must be performed fault tolerantly. That means we need to do them in a way that doesn't allow our errors to spread too widely or multiply. And when assessing fault tolerance, it's not just about how am I doing the error correction on one instance of the code or how am I doing a particular gate. That idea of fault tolerance is how am I doing the whole circuit, the whole thing that is simulating, or whatever we want to call it, that is executing this large-scale ideal algorithm that I want to do in a fault-tolerant way. That fault tolerance, that ability to put it all together, is an all-of-circuit property, not just something that you can say, do I have a fault-tolerant logical qubit, or do I have a fault-tolerant gate? So there's a bit of subtlety there, and as I said, Jungwon gave a nice explanation of that in some detail, and looked at some recent experiments in the light of that statement. Dan Gottesman has a great paper that really set out that framework. So through my talk, I'm going to just put up some of these observations, and this is, as I said, sort of my view on what are some of the interesting questions that theorists in quantum error correction and fault tolerance should be, or could be thinking about right now. How do we characterize the fault tolerance of a logical qubit or a gate, a logic gate? That actually requires a lot of care, and it's only now that we're starting to see some real experiments done that I think these questions, these issues are really coming to the fore. It's giving theorists like myself, who've been in the game of characterizing errors for a long time, it's suddenly giving us pause to say, oh wait, am I really capturing all of the fault tolerance properties of that gate when I'm looking at this experiment, or is something missing there? Is that gate now of the type that I could stick that into a larger fault tolerant quantum computation and really see some gains over the physical error rates? So needs some care. There's a lot of open questions, and I think that's going to be the main topic for several of the talks tomorrow. Okay, so I talked a little bit there about architectures. So let me describe what that means. What are we talking about when we say a fault-tolerant architecture for quantum computing? So again, we're going to step back, take this whole-of-circuit approach. So I pick some algorithm I want to run, Shor's algorithm or something like that. It's got a certain number of qubits. It's got a certain depth. I also look at the hardware I have available. I might have characterized that physical hardware with fidelities of my qubits, fidelities of my physical gates, as well as some constraints, such as whether I can interact all of my qubits, or do I need to directly, or do I need to shuttle them around? Do they have some geometric constraints? Lots of other constraints you can have in hardware. I take those things together, and I pick a fault-tolerant architecture, which is a choice of code that I'm going to use. I need a gate set that's and not just a gate set, as I said, a method for how I'm going to do all of my logic gates. So it's not enough to say, oh, I'm just going to do T gates. I would need to figure out how am I going to do them fault tolerantly within my architecture. And then I'm also going to need to set the distance. When I say choice of code, that might be a code family. I'm going to pick a specific distance in order to try to solve the algorithm that I'm interested in. So when I say a fault-tolerant architecture, it's all of these components here. And then when you have that, we can sort of estimate, okay, how hard is that going to be? The threshold theorem says that we can execute these large algorithms using noisy hardware, provided we're below the threshold, with not significantly more resources. But what that means in practice, we actually have to look at what are those constants, what are those coefficients for that simulation, and actually they can be quite significant. So let's have a moment to think about what are the resources we need to implement this fault-tolerant implementation in practice. So there's good news and there's bad news. And I think this slide is sort of capturing the perspective that we've had for the past maybe almost 20 years in the field of fault tolerance. The good news is that we have some quantum error correction codes which seem to provide a path for doing fault-tolerant quantum computing, meaning that they have reasonably high thresholds such that we can expect to be able to build hardware that is going to be able to operate below that threshold. Standard example here would be the surface code, and it has thresholds, again, around 1% or a fraction of a percent. And 20 years ago, people sort of thought, oh, I think I can build hardware that's going to be able to beat that threshold. And now we routinely see that in many different hardware platforms, that there are claims that all of their operations are falling below that threshold for fault-tolerant quantum computing. What do they mean by that threshold? They mean one based on the surface code or a related code. More than that, topological stabilizer codes such as the surface code can get by with just nearest neighbor coupling, so we don't need long-range interactions. And this seemed like it was desirable for some hardware platforms. This is a picture of a design schematic for superconducting qubits. And they have couplers that allow you to interact neighboring qubits, but it is hard to interact distant qubits. You would have to do that through some sort of chain of interactions between those distant qubits. But the picture there was broadly good. We have codes like the surface code and some other related ones in a family where we have thresholds that we think are achievable. The geometric constraints and other constraints imposed by the hardware look like they're going to be compatible with an architecture for fault-tolerant quantum computing. And then some recent work on things like bosonic codes is even giving people more optimism that we really are in a good position when it comes to codes. So that's the good part of the story of the past 20 years. But we've probably all heard the bad part as well, which is the overheads associated with it. So the threshold theorem says, okay, you can simulate your perfect circuit with a noisy circuit with a little bit of an overhead. But what does that mean in practice? When you crunch through the numbers, actually, those numbers look horrible. When you say, okay, I'm not interested in asymptotic, polylog n overheads. I'm interested in, I want to run Shor's algorithm on instances of interest. I want to say how many qubits am I going to need in order to build surface codes big enough to protect for errors in the type of hardware I'm describing here. And the answers are astronomical. You will need thousands, if not millions, of physical qubits for each individual logical qubit. That sounds horrible, but it gets worse. To do the error correction in those codes, we need to measure many times, repeatedly, and that adds a time overhead and a bunch of complications. Then you say, well, that's just thinking about those codes as a memory. What if I want to do quantum logic? Okay, there's some gates where that's not a significant overhead on top of memory, but there are other gates, such as non-Clifford gates, where those overheads are also astronomical. And okay, what does that mean when you run through some numbers? That's not the reference that I'm referring to here, but also from Craig Gidney, an estimate with some reasonable assumptions on hardware that to run an interesting instance of Shor's algorithm, you would need something like 20 million qubits and 8 hours. That seems really hard to build. So the good news is it seems like we have codes where we can reach the threshold and implement them in practice. But if we were to take that approach, it's going to be ghastly in terms of the types of overheads we need. Okay, so that puts us in the position where we are now, where people say quantum error correction is becoming possible. We have experiments demonstrating many of the elements of quantum error correction and fault tolerance. But to actually now do this at scale is going to be very challenging. Okay, I used a little bit of jargon in there, so let me see if I can flesh out some of those details. Okay, so here just a bit of the jargon around the standard approach in architectures to doing quantum logic. So we have logical qubits in codes. We might have many such codes on which we're now thinking of doing a computation. Okay, let's do a categorization about how we're going to do quantum logic gates. Once you've picked a code, it sort of gives you a classification of easy or fault-tolerant, naturally fault-tolerant gates, which are the so-called transversal gates. We can implement those logic gates. Remember, that's a gate between a logical qubit in a code and a logical qubit in another code, for example, a logical CNOT gate. Gates acting on the logical qubits. We can implement those just by doing individual gates on the physical qubits that make up that code. That sounds easy. To make it fault tolerant, you still need to do quantum error correction, and that might involve several rounds, so there's some complications there. But that's a straightforward way to do a fault tolerant gate. If you look at how errors behave in that type of gate, they don't spread or multiply uncontrollably. The challenge, though, is that we can't, there is no code for which you can find a universal set of gates for quantum computing that can all be done in this transversal way. So no matter what code we pick, we're going to have to do some gates, at least one gate, in a different way that can't be done transversally. And they need some more complicated constructions. Examples include injecting magic states, and so we need to distill those magic states through some complex techniques. There's a bunch of other approaches, though magic state distillation is the one that's been explored the most. And those can come with some very significant time overheads. How long is it going to take for me to do all the stuff I need to do just to implement that logic gate? Okay, so this at the bottom is meant to just be a helpful summary for those new to the field. If we pick, for example, stabilizer codes, that's a common class of quantum codes. You might say, how do we figure out what are the easy gates and the hard gates? We have a lot of codes where Clifford gates, such as Hadamard, C-naughts, phase gates, those can be done in this easy way, this transversal way. However, we then need to add something else in order to get a universal gate set, because Clifford gates are not enough. Here is my simple summary. Clifford logic gates, easy, fault tolerant, in some sense, sort of classical, because if you're just doing Clifford circuits, you can efficiently simulate everything. In order to be able to do interesting quantum algorithms, we need to add some sort of non-Clifford gate, and they are costly and more difficult to do. So when you're designing a quantum fault tolerant scheme, you need to think about okay, where am I putting all of my resources? Because of the sort of classical nature of these Clifford gates, often we can sort of just compile it away and do that aspect in software. And it really puts the focus on how do we get those non-Clifford gates in the most efficient way possible. And much of the work done on architectures in the past decade or so has been focused really on that issue. How do we get nice, efficient ways to do the difficult gates in fault-tolerant quantum computing based on stabilizer codes such as surface codes or other gates? But just an observation is that this simple classification was done because it was nice theoretically. The idea that we're going to stick with stabilizer codes, we're going to use codes that have nice transversal Clifford gates, but we're going to then have to think in clever ways about how to do a non-Clifford gate. That construction, that division of things was done just for its theoretical simplicity. So there might be better ways to do it. And then also, when we start thinking about doing things in practice, well, okay, let me not even go into details there. What's that?
What's a better way to do it?
What's a better way to design fault-tolerant architectures than with this division of Clifford versus non-Clifford? It's a good question. I mean, I don't have an answer. I would say that is a great question to put out there for the theory community. I mean, we do have other approaches, other computational models. For example, you know, we know that you can do universal quantum computing with just Hadamards and Toffoli gates. And there's a theoretical result where no one, I think, has worked too hard on looking at how we would do fault-tolerant implementations of well, within that model, where I have fault-tolerant Hadamard and Toffoli gates. You certainly wouldn't want to go ahead and use the stabilizer code construction, because I think you would just inherit all of the inefficiencies that are associated with the standard scheme. You'd have to do a magic state for that Toffoli gate, and even the Hadamard in the surface code is a bit of a trick. So I think you could go back to the beginning and say, what types of codes would I use if I wanted to try to think of fault tolerance in that computational model? And that's just an example. But I think it's worthwhile for the community to look for other potential examples. Yeah?
What do you think about code switching possibilities?
Yeah, code switching is another one of those, I would say, complex constructions to make things fault tolerant. And I think, yeah, I mean, I like code switching constructions. They also come with a lot of overheads in terms of having to switch from one code and then back again. I think there's still a lot of work to be done about exploring the full range of different ways that we can do gates and really comparing what are the different overheads in those approaches, and not just asymptotic overheads, but what are those overheads in practice, in the regime of interest. But yeah, I don't mean to suggest that magic state distillation is the only way to do it. There's in fact a whole variety of ways. Okay. I have talked a bit about the surface code, and so let me just take a slide or two and give you a few more details about fault tolerance using the surface code. Because again, there's a bit of jargon in here that I think will come up a few times during the other talk. So I'm not going to go through and define the surface code and all of the details of it. I know many of you have seen that before. But let me tell you about how this process that we showed before about constructing an architecture works when we decide to pick the surface code. So as I said, the surface code has a nice high threshold and local 2D arrangement. It's geometrically local in 2 dimensions. So that's a nice desirable property of codes. But just picking the code doesn't tell you how to do quantum computation. How do we do gates? Even with once we've picked the surface code, there's many potential ways that you could do your quantum logic. I wrote here, given a surface code, the approach that gives the current lowest overheads is lattice surgery. And I was just questioning this morning whether I'm completely sure that's true. I think it is. Lattice surgery is certainly the most explored in terms of people working out explicitly what are the overheads for gates. But if anyone knows of some developments that are giving lower overheads, I'm not ruling that out. I'd love to hear about it. So let me just cover what lattice surgery is for a minute, as I expect it might come up a few times. Okay, so here's how you build a fault-tolerant architecture out of surface codes. You need surface codes in patches. Here, I mean, the patch is even denoting the different types of boundary conditions for that surface code. This construction, I mean, lattice surgery goes back quite a long time, but really the state of the art is outlined in this paper by Daniel Latinsky from 2019 with the cute name, A Game of Surface Codes. And there's been a few modifications and innovations since then, but I still go to that paper as the basic ingredients of the best construction at the moment for a clear, here's how I would do fault-tolerant quantum computing with the surface code. How do we do that? Well, the first thing you do is you convert your logical quantum circuit into a so-called Pauli-based computation. That means I think about doing my circuit not by applying C-naughts and T-gates and so on. I do my circuit through a sequence of multi-qubit Pauli measurements. It's equivalent model for computation, but there's actually a lot of details washed into that step about how do I do all of my T-gates in the most efficient way if I was trying to minimize, for example, the T-depth or the T-count or whatever I'm trying to optimize. Okay, so we're in a model where I have a bunch of surface codes, and now I want to do multi-logical qubit Pauli measurements. I want to do Pauli measurements on many surface codes at once. And that's what lattice surgery involves. We have a bunch of these patches. We have to make ancilla that allow us to facilitate a multi-qubit Pauli measurement between a bunch of the patches that ancilla touches. And then I can do the logical multi-qubit Pauli measurement through a bunch of physical qubit measurements, which are not all that different from the measurements I do in quantum error correction in syndrome extraction for the surface code. I'm measuring a bunch of local Pauli operators. But there's a bunch of options in how to do that. Options for trading space and time. Options for splitting up how I do my distillation versus how I store my data with different overheads. The point is there's a bunch of options in there. Once you pick your choices, it allows you to very explicitly compute numbers like how many physical qubits do I need to run this algorithm? How many time steps do I need to run this algorithm? Okay, so just some observations about this. That surface code gives you an explicit scheme, has that nice property of high overheads and geometrically local properties, but it's extremely costly in terms of that overhead, and I think we should be asking the question, can we do better? So there's lots of opportunity here for disruption. There's different types of topological codes. There's quantum LDPC codes, which I'm going to talk about in a minute. There's also, as I said, more work to be done on codes with different types of fault-tolerant, naturally fault-tolerant gates. Okay, so I think this will be the last part of my presentation, which is just covering what is, I think, got the field quite excited in recent years, which is the idea of using low-density parity check codes, quantum low-density parity check codes, for fault-tolerant quantum computing. Okay, so just very briefly, what are low-density parity check codes? Well, the surface code is an example of a low-density parity check code, just not a very good one. It's low-density parity check as in the parity checks, which are the check operators that I measure on the code, are acting only on a fixed number of qubits, in this case 4, at most 4. So that's a nice property of quantum error correction. In fact, we think we need that property in order to have nice high thresholds. The downside with the surface code is no matter how big I make that surface code, I can make its distance, its error correction properties better and better by making it larger. But I only ever encode one logical qubit in that code. When we talk about quantum LDPC codes, as I said, the surface code is an example, but not a good one. Good ones are those that can encode many qubits in many logical qubits in a code. And as I scale the code, I think of code families, and as I scale that to larger and larger sizes, I want the number of logical qubits also to grow. Okay, so here is a summary that I took from the error correction zoo about where we're at and a bit of the history of LDPC codes. Going back to, as I said, the first one, Kitaev's torque code put on a surface is the surface code we've been describing now. Has a couple of deficiencies. One is that the distance doesn't grow with the number of physical qubits as fast as you would like. And number two is that the number of logical qubits doesn't grow at all with the number of physical qubits. But that's 25 years ago. Lots of work has been done since then on improving those parameters. And what is fantastic is that just in the last few years, we have seen some codes that fall within this parameter range of good codes, meaning I have code families. I think of the number of physical qubits. What's the distance? It's growing with n. What's the number of logical qubits? It's also growing with n. Okay, so that's fantastic from the perspective of saying, okay, we found some very interesting potential codes that might be used to lower some of these overheads, but can we make that work in practice? Just having a code doesn't give you an architecture for fault-tolerant quantum computing. Okay, my one physics slide. I was warned about talking about Rabi frequencies and so on, but here's a one physics slide which suggests, okay, well, people say the surface code is nice because we have nearest neighbor interactions, and that's what you need when you're building hardware. Is that really what we need? Well, there's lots of recent results in many different systems that says that doing long-range interactions is possible in neutral atoms, in superconducting qubits, in spin qubits, using photons, a range of other approaches. So having nearest neighbor interactions is not an explicit requirement, though also the caveat that just because we have a long-range interaction doesn't mean we have all-to-all connectivity. But certainly geometrically, local gates is not sacrosanct. Okay, so here's the key question. Is there a low overhead architecture based on high rate quantum LDPC codes? And it's interesting, Dan Gottesman asked that question now a decade ago, long before we had these good quantum LDPC codes. He said, imagine they existed. Now, what would you need in order to turn that into a fault-tolerant quantum computing scheme? Now we have codes that satisfy his criteria. And I haven't put up any references for this, but for a number of those code families that have been discovered recently, we have at least some good positive results on having reasonably high thresholds and fast decoders. But I would say in general, the focus of most of that work has been on asymptotics, including Dan's work, sort of saying, can I think about constant overheads? What's that, what are the additional extra number of qubits and additional time I need to do fault-tolerant quantum computing asymptotically? The real question I would say for the field is, what does it mean in the relative regimes of interest when I want to get algorithms of particular size running on hardware with particular error rates? And it's just in the last year we've seen some of the hardware teams starting to ask some of those questions. And for example, I'm sorry, this is a bit poorly laid out, but a recent paper by IBM suggesting that if they could, on their device, have some interactions which connect distant qubits, and this is just one such interaction connecting qubits across the chip, but they need many such interactions. But they can implement a particular instance of an LDPC code on a chip with that type of connectivity, and they see a pathway for doing fault-tolerant quantum computing with lower overheads than if they had done that with just the surface code. Of course, they need to figure out how they're actually going to build that and what will be the associated error rates, but that does sound very exciting. And then out of Misha Lukin's group at Harvard, also some results using their neutral atom platform, which allows you to do much more interesting connectivity amongst the atoms in a code. And they've given now an explicit scheme for doing constant overhead fault-tolerant quantum computing. There's still a lot of work to be done on doing your fault-tolerant logic gates in these types of codes. And here I want to highlight some work we did at Sydney. Larry Cohen was the lead author on that. He worked out a way to do lattice surgery and the logic gates involved in lattice surgery, but for LDPC codes rather than just the surface code. Now, that's not the full answer. That gave some significant gains in terms of qubit counts, but I would say it's clear from the construction that there's lots of inefficiencies in Larry's scheme for doing those logic gates, and there's lots of room for improvement. Yeah?
So can you say something about how IBM proposes to do these long-range interactions in superconducting qubits, I assume?
Am I allowed to give a physics answer?
Yes, of course. I was hoping you would.
Yeah, so I don't know a lot about the details. I mean, there's some IBM people here.
Yes, and we have 2 IBM talks after lunch.
But yeah, the key would be to put in some long-range couplers on the chip. And so, I mean, when making good question. What's the density of it? You certainly do need a lot, but I mean, what is the density of them? I don't know that off the top of my head.
I thought they wanted like 2 planar layers that they can build on top of each other, and with that like 3D geometry. That's like my rough understanding.
You're exactly right on that. In that they're taking that, in a sense, you're looking at one layer, which is your nearest neighbor interactions. And then you have a second layer which involves these couplers connecting more distant parts on this chip in a way that doesn't have to cross, and that provides the connectivity.
Just one permutation would do it. So is that the idea? Because with the second layer, you would, I assume you get one extra. You just get a permutation of the qubit or something.
It's definitely just one extra layer. Yeah, how do I understand that in terms of permutations? I'm not sure. I shouldn't speak too much about the details of this because I don't know.
I mean, I can comment
just
briefly. Right, so every qubit will be connected to 6 others. And what's important is that for the couplers on chip, they really can't be too long. So it is still kind of quasi-local. I mean, it's just that the connections can be long enough that if your code block size is small enough, they're effectively, you can effectively reach the other qubits on the chip. But then there'll be a limit to how long these couplers can be on chip, and they want to do something else. But they could be routed on multiple layers.
Sorry, so but if you're staying pretty local, shouldn't there be more asymptotic improvement?
Well, that's true. So there will be some limit to scaling the local couplers, and then you can have longer range couplers that couple chips.
But maybe that gets to the point, which is, or at least one of the points I was making, that you can ask questions about the asymptotic scaling of these things, but when looking at reducing the overhead for fault-tolerant quantum computing, we often have some specific code distances in mind. And say, how can we optimize this for code distance of 8 or 10? Because we think with the hardware error rates we have now and a code of that size, we're going to be able to do fault-tolerant quantum computing to solve problems of interest.
It's a different question.
Yeah, but this. Okay.
Okay, I'm out of time, so let me just wrap up here with just some of my observations about quantum LDPC codes. Okay, so I feel that there's still a lot of work to do here, but that low overhead architectures for fault-tolerant quantum computing based on either these new quantum LDPC codes or ones that have not yet been discovered, that's within reach. But there's quite a bit to do in terms of translating those general properties of a code into specific implementations. And here I think it's going to change the nature of research in this field a bit. For a while, there's almost been this convergence that no matter what architecture you're working on, whether you're working with ions or spins or superconducting qubits, we're all doing the same thing, which is surface code and lattice surgery. I think this fact that connectivity is going to be front and center to all of these considerations. It's going to determine what codes you can use and get benefit from. That's going to likely lead to a whole sort of divergence of approaches, that the neutral atoms people may go one way, the superconducting qubit people might go another way and use quite different codes simply because it's more suited to the constraints of their hardware. So that means that this is a great opportunity for the theorist, because there's going to be many different directions, many different hardware teams pulling you in different directions, and many different problems to be solved. I think that's a good place to stop, even though I think I have about 100 more slides. So I'll end it there. Thank you.
Thank you very much, Stephen, for this very nice overview. I'm sure they have some more questions.
Yeah, thanks. Very nice talk. On the last part of the quantum LDPC codes, I mean, how much flexibility is there in actually doing logic with quantum LDPC codes, and that the notion of a boundary is very different in LDPC codes compared to like topological codes? So what lattice surgery means is somewhat different. So can you elaborate on the potential pathways to do like quantum logic with QLDPC codes?
Absolutely. I can tell you just a bit more of this result of Larry's, which is an attempt to generalize lattice surgery for LDPC codes. And the term lattice surgery itself is now being horribly abused because there's no lattice, and the idea of doing surgery, with boundaries and so on is out the window as well. But the general principle that we need to construct ancilla that allow us to reach in to either within one LDPC code or across multiple LDPC codes and do these multi-qubit Paulis, multi-qubit logical Pauli measurements that are part of lattice surgery. What kind of ancilla do we need, and how do we build ancillas that let you do that? So Larry's construction gives you that, but in many ways, it's not the it is an ancilla that lets you measure the required operators on LDPC codes, but the ancilla itself is not LDPC-like. It's not, it's very surface code-like. So its scaling, its properties are not taking advantage of the gains that we would see from an LDPC code. And that's one of the things I think is a big open problem is how do we do the logic gates with ancillas that will really let us exploit those gains in the logic as well as in the code size themselves, the memory, exploit the gains that we're seeing from these new LDPC results.
Any further questions?
You mentioned before that the surface code is an LDPC code, but there's also a distinction that you're doing between those two.
Yeah, so often when I'm talking about LDPC codes here, we're thinking about good ones with these nice properties, nice scaling of distance, nice scaling of logical qubits. They don't even necessarily have to be strictly good in that sense. I mean, I think what we're making a distinction between surface code, which is almost the worst in terms of those code parameters, and a class of codes that improves on the property, significantly improves on the properties of the surface code. So that's what I mean in this general part about quantum LDPC codes is ones that are better than surface code in either distance or number of logical qubits.
All right, then perhaps one last question over here.
As your system scales, how good is the assumption of uncorrelated error for these things? It seems like it's pretty central to the construction of these codes, but as you have many more qubits, like 20 million qubits, the levels get quite close.
So sorry, the assumption about uncorrelated errors. Yeah, well, I mean, and so that really goes right into, okay, what is that assumption? It's right in our threshold theorem. I mean, there's a couple of variants of the threshold theorem, but all of them are demanding some niceness properties of the noise, which is that it has to be sort of close to uncorrelated. Now, when we start to think about, architectures like here, where we're now having qubits not just interact locally, but maybe have some long-range interactions. Yeah, you can just see that that's a channel for adding all sorts of noise that's spreading in a very non-local, highly correlated way right across your device. What is that noise going to mean for doing fault tolerance in those types of codes? Yeah, that's absolutely a great question, and I would say we have to build those types of devices and do the types of noise characterization that's going to explore what is the actual noise in those experiments. Can we keep it'll be okay if we can keep that noise down below some floor, but exactly what that is, I don't know.
Right. I think with this question, this gives already an outlook to tomorrow. Let's perhaps close this first morning session. Thanks, Stephen, again, and then enjoy a coffee. And we reconvene at 11:15.